Okay, so hi everyone. Welcome to our weekly seminar here at the Institute of Astrophysics in Crete. Today we have the pleasure to have with us Jed Homer. Let me briefly introduce him. Jed is a PhD student at the University Observatory Munich, LMU in Germany. And his studies involve machine learning and cosmology as well. In particular, his interest focuses on the use of generative models for Bayesian inference problems, especially when a theory model or analytical likelihood is not available. And since we are going to learn a bit more about this, without any further ado, the floor is yours.
Great. Yeah, good afternoon, everyone. Thanks for having me. I'm Jed Homer. Yes, I'm a PhD student working with Oliver Friedrich and Daniel Gruen. And yeah, today I'm going to talk to you a little bit about a paper I put on the archive December of last year, talking a lot about, the use of simulation-based inference and therefore generative models in physics and astrophysics. So yeah, the story really starts today with, how we fit our models to our data. So here I'm just going to,
Jed, sorry, we are not seeing you sharing the presentation.
Okay, one moment. Let's see. Let's see. So you can see now, is this okay?
Yeah, perfect.
Perfect, thanks. So yeah, our story today kind of starts with how we fit our data, how we fit our models to our data. So here I'm just, quickly introducing, a little bit Bayesian statistics and, notation for today. So, we obviously want to assign a posterior to the data that we measure. So this gives us, the probability of our model given the measurement that we take. As you well know, this depends on the likelihood and the prior that we assign to our data. And it's very common in cosmology to, take some measurements in a galaxy survey and assume a Gaussian likelihood for these measurements based on, maybe some physical evidence we have, or, arguments related to the central limit theorem. And, this Gaussian likelihood depends obviously on a covariance matrix, which describes the uncertainties in our data, the scatter around the mean. This, also depends on a precision matrix, which I'm, being very, I'm formally making a difference between those two objects here. And of course, this model, psi, as a function of the parameters we're trying to constrain from our data, pi here. So if you've seen, many papers recently about simulation-based inference and, sort of the rise of generative models being used in in cosmology when we don't know our likelihood function. So, why else would you want to use SBI? Well, your likelihood itself you have physical reasons to believe that this is not a Gaussian distribution and you don't actually have a functional form for this PDF available. Your model for your statistic as a function of, the parameters you're trying to measure, maybe a complex nonlinear function of the parameters themselves. And, maybe the statistics inaccurately predicted in simulations. And also the covariance itself, this covariance matrix may actually depend on cosmology itself, which is, a very expensive problem computationally. So today, basically, I want to talk a little bit about this paper we've done and, about SBI in general. And generally, I want to just answer the question, does SBI do what it says it does, given these very, large problems we have as cosmologists, that we face in our analyses. So, to start this off, I want to talk a little bit about covariance matrix estimation. This is, very briefly talking about, 20 years of research into this. But what I'm going to talk about today is a quite specific, but very general, very common situation we face, where we have a suite of simulations, for example, Cosmogrid, Illustrious TNG, or Quixote, and we measure our data covariance for data that's Gaussian distributed by basically using this sample covariance matrix estimator I've just written down here, evaluated over NS different realizations of our data, simulated data. So there's something very important that I need to show you quite quickly, but this is basically what's known as the Dodelson-Schneider effect. So this was, written in a very important paper from 2013 by, Scott Dodelson and Peter Schneider. And basically what they showed us is that the noise in this covariance estimate, given that we have only a finite number of simulations to estimate this data covariance with, this is obviously a noisy estimate of the true data covariance, right? And, downstream, when we derive our posterior, given this Gaussian likelihood, this causes actually two problems. So the first problem is we have some noise in the width of our likelihood contour and therefore in our posterior width as well, due to the fact that we only have a finite grid of simulations. And the naive inverse, inverse data covariance, which is obviously, the precision matrix, as you may know, is a good estimator. If I'm saying here, it's a good estimator, basically, if the number of simulations we have compared to the number of bins in our data vector is much larger than the number of parameters we try to infer. So on the right here, I have a figure for a parameter space, and in blue, I basically have a data covariant, a posterior covariance from derived with a noisy, simulation estimated data covariance, and then I've debiased the width in this estimator for the precision matrix based on this Hartlap factor, as you may know. In black, I have the true contour here if I knew the data covariance, and you can see that there's a very large noise in this, very large expansion of the contours due to this data covariance, noisy data covariance. So the second problem actually that affects our posteriors that's much more significant is the location, where in the parameter space we actually end up in with, our posterior being centered around. And what they find is basically, the precision matrix estimator derived from this noisy covariance is a good estimator only if the number of simulations minus the number of data points we have in our data vector is much larger than the number of, bins in our data vector that we measure, which is a much more stringent requirement that it's not necessarily met going forward into future galaxy surveys. So, if you remember just one thing for today, let it be this Dodelson-Schneider correction, which corrects your posterior for the noise in this location of your posterior contours due to the noise in your data covariance. So they just have a very simple derivation here for Gaussian linear models. And what they're basically saying here is, the true posterior width given your noisy data covariance is given by this factor in the square brackets, which multiplies the true posterior covariance if you had access to the data covariance here. And this correction is valid for basically if you have a high number of simulations, much more than many more simulations than bins in your data vector, and this in turn is much larger than the number of parameters you're trying to measure. So yeah, in practice, there's a very nice paper by Will Percival and other authors from 2021, and they basically derive correction to the posterior based on accounting for the noise in the data covariance and its scatter around the true data covariance under the assumption of Gaussian distributed data. And basically what they derive is basically a correction to the coverage that accounts for this unknown data covariance. And what you're seeing here in this plot is basically the true posterior if you knew your data covariance, the Sellington and Heavens correction with a Hartlap debiased precision matrix in this orange contour. And then finally, this blue contour that expands due to the noise being accounted for in the data covariance. So it's accounted for in the posterior in a rigorous Bayesian treatment. So you see that you lose information, which makes a lot of sense, right? You're not using the correct data covariance there in your likelihood. So interestingly enough, for this Gaussian likelihood case with a linear model, this is actually the solution, this blue contour here, that a machine is aiming for example, in a simulation-based inference analysis. And I'll talk a little bit more about that in a moment. But, back to what we're talking about today, this paper we wrote, we were asking questions about SBI. So what I'm showing you here is basically a variety of contours from a bunch of different ways of basically, correcting for your noisy data covariance. So in black, we have the true contour, and this black cross signifies the true parameters we're trying to basically measure. And basically in red, this is, not accounting for the noise in the covariance at all with a very low number of simulations, so only 500 simulations given a 450 dimensional data vector. And you can see that we're very, very biased and like wildly underestimating the posterior width here, so very confidently wrong. And then in blue is the kind of quite a classic approach of just using a data covariance, or sorry, a precision matrix in your likelihood that's corrected for with a Hartlap factor. And then in green, this is actually the kind of state of the art from this paper I just showed you with this Dodelson-Schneider correction applied plus the Hartlap. It actually turns out that these two approaches, the Dodelson-Schneider plus a Hartlap correction, actually turn out to be equivalent in this exact setup I'm using here. So the relative size of the number of simulations I have and the size of the data vector I measure. So, a question we can ask about SBI using these generative models to fit a likelihood when we don't know our likelihood is, which posterior would SBI obtain given this inference problem here? So here I'm just drawing a pink cartoon contour here. And I think there's two questions you can answer that quantify, exactly what SBI is doing. The first is basically, is this pink contour drawn in a set of repeated experiments using SBI? Is the posterior width, marginals, for example, is it inflated with respect to a Gaussian likelihood analysis for the same number of input simulations we use to estimate the covariance when we know our data likelihood? And then the second question I think we can ask, is does SBI adjust this posterior width to fix its coverage such that we infer the true parameters with the correct probability, given that given the effects that I've shown you on the likelihood when you don't know your data covariance, and we don't supply SBI with the data covariance either. So, while we think about these questions, there's one thing to keep in mind. With SBI, we fit this data covariance, we fit the model as well, and the likelihood, quite literally the functional form of this likelihood simultaneously. So where before I've shown you these Gaussian likelihood analyses where we just estimate the data covariance and have some model, and we assume the form of the PDF, SBI does all of this at the same time. So it's, quite a different approach, but certainly potentially more powerful. So now I'll talk a little bit about how we, kind of challenge SBI and testing these likelihoods that we fit with these generative models. So, what we do here is just a very standard experiment with SBI here. So starting from the left, basically, in one repeated, one of these many repeated experiments, we sample some true parameters pi. We measure a data vector from the true likelihood given the true data covariance and the true model evaluated at the true parameters. We then compress this data vector, which is very much standard practice in cosmology and SBI as well. And then basically we train a generative model on a suite of simulations, kind of Latin hypercube of different cosmologies to obtain a posterior here. So in red, I have this true posterior, just a cartoon, of course, but in blue, I have the true, posterior obtained with SBI centered around some estimated parameters here. So if you've seen the paper, you'll see that we, test a bunch of different experiments here, mostly relating to the compression. And I'll explain why we kind of change just the compression part of this whole experiment later. But yeah, basically what we do, we have two options. You either have a linear compression, which you can think of as MOPED or PCA, for example. And then basically within this linear compression, we have the case that we estimate the data covariance. So input into the whole experiment would be double the number of simulations in this case. And the reason for that is you estimate your data covariance with half of those, and then the other half of those simulations you train your generative model with. And then in the case that we know the data covariance, we only need to train our generative model. So we use half the number of simulations, just NS there. And obviously for this Gaussian linear model, this linear compression here is completely optimal. You can't do better than it. For example, if you were using a neural network here, as we show on the right, with double the number of simulations to train the neural network doing the compression, and then to train the generative model to fit the likelihood. So, at this point, there's a few questions I think, I've been asked before. And, the first of these is, well, yeah, there's just a point really, but, you need the data covariance here to parameterize this optimal linear compression that conserves the information in your data. And, why not just use a neural network? We've seen that these can be very effective in many branches of physics, and it's not implicitly inverting a data covariance, which is what amplifies the noise in the original estimator. So why not do that? Well, I'll talk about that in a bit. And also, why not use field level, which doesn't use compression? Don't compress our statistics, just fit a generative model to it because we've already simulated them. You can do this, but actually you're not escaping the effect of covariance matrix estimation there. The problem here is not actually the data compression, it's the fact that you don't know your data covariance here. So you're not technically avoiding that in this case, and you still have the same number of simulations here. And compression, doesn't simply remove the noise in this noisy data covariance, and your posterior truthfully is inflated by your ignorance of the true data covariance here. So just a few points there, but yeah, so here basically I have just a kind of spoiler in one universe. So this is just showing you the results of applying SBI compared to a Gaussian likelihood analysis in one repeated universe, well, one repeated experiment or one universe. So basically on the left, we have a Gaussian likelihood analysis using this Dodelson-Schneider corrected posterior and the heart lap correction to the precision matrix. So you might not be able to see this, but it's supposed to be a green contour on the left compared to the true 1 sigma contour of the Fisher matrix here. So the true posterior compared to a Gaussian likelihood analysis where you don't know your data covariance and you only use 600 simulations there. So this is obviously centered around those estimated parameters. And you can see just that, you can see an inflation here relative to the true posterior. So on the right, we have, two simulation-based inference analyses to compare to both of these posteriors on the left. The first of these, this magenta contour, is using this optimal linear compression, but with an estimated data covariance here. And then the second is using a neural network for the compression here. And you'll see actually, despite inputting double the number of simulations relative to a Gaussian likelihood analysis, you can see that the magenta contour and this yellow contour representing the neural network compression are pretty significantly inflated relative to this Gaussian likelihood analysis on the left. So, this is, I'll back this up, I'll back up this result in a moment, but, SBI is aware of this Dodelson-Schneider effect, but it's inefficient in its response. For double the number of simulations, you have significant posterior inflation there. So I'll show you the kind of results from these repeated experiments here. So this is a lot going on in this graph. Just look at the yellow part because it's a linear model and all these parameters, are linearly responding in the data. So you can just look at the yellow part for now. So this is basically just asking, does SBI recover the posterior widths it should, given the simulations we put in? So on the x-axis, we have the number of simulations input to the experiment. And then on the y-axis, we basically have the marginal posterior width here. So starting from the dashed yellow line, horizontal yellow line, this is the Fisher posterior width here. So the width of the posterior if you knew your data covariance. And basically we compare this to the crosses here, which are all on the line here. So these crosses come from the measured posterior widths over repeated experiments. Given that we use the optimal compression, we fit the likelihood with SBI, and we know the data covariance here. So it's kind of a control experiment here. So if you give SBI the data covariance and an optimal compression, it's recovering the correct posterior widths, regardless of the number of simulations you give it. So this is nice. So next, if you look at this kind of dotted curved line, this is the posterior width predicted by the Dodelson-Schneider effect. So if you don't know your data covariance, this is how much information you lose relative to the dashed line representing the true posterior. And then you can kind of barely see them, but there's basically these dots that are sort of curving down towards this dotted line as the number of simulations increases. And these are the posterior widths reported from basically supplying SBI with the optimal linear compression, but a noisy data covariance. So we use a different data covariance for each experiment, obviously. And each of these points is reconstructed, is measured using 200 independent experiments with, independent data covariances and training and all of this. So basically what I'm saying here from this plot, and you can see it in the red dotted lines versus the red dot points, and the same for the purple, is that basically for low numbers of simulations, SBI is actually systematically losing information relative to the correct solution to this inference problem when you don't know your data covariance with a Gaussian likelihood here, given by the dotted line. And, it's important to note here, the value on the x-axis for the experiments where you don't know your data covariance is actually supposed to be doubled, right? Because I'm only plotting for the simulations input to the generative model here. So there's additional simulations used to estimate the data covariance for these experiments where you don't know your data covariance. So the other part of this picture, which I spoke about, is the posterior coverage. So this is, nothing too crazy going on here. Basically, you have on the x-axis for these graphs, the number of simulations input to the experiments. And then on the y-axis, you basically have the fraction of experiments you recover your true parameters within the 1 or 2 sigma contours given by the blue and green lines here. So yeah, bit of a boring graph, but all this is saying is that basically SBI assigns the correct probability in its credible intervals for the posteriors, right? And on the left, this is basically if you don't know your data covariance, and on the right, this is if you do know your data covariance. So this is good. So let me just show you quickly some plots of what this looks like in practice. This is with using 2 types of density estimation algorithms, which you can read about in the paper. But they're, using normalizing flows, which is standard practice by now. So basically on the rows, I basically have the number of simulations input here. So basically the blue contours in every plot are when you don't know your covariance, and when the red contours are when you do know your data covariance. So, the top row, you can see significant posterior inflation in both of these cases, regardless of the algorithm we use to fit the likelihood. And then in basically the bottom row, you see the posteriors are recovering the same posterior widths approximately, and this is very close to the true posterior widths given the high number of simulations here. So I've just shown you quite a lot. So, what is SBI actually doing? The coverages are correct. We obtain the correct coverage for the 1 and 2 sigma credible intervals, and the widths are inflated, as I showed you before. But for low numbers of simulations, there is an additional posterior inflation. So, we're using this to say basically that SBI knows about this Dodelson-Schneider effect, and it actually corrects for it here. So yeah, that's basically the main result for the day today. I mean, I have some other things to show, but I think, it's nice to kind of keep it a little bit short here. But just to go over the kind of main insights here, I think, SBI, when we give it the optimal compression, the true model, and when we train, do all of these experiments with Gaussian likelihoods and these sort of cutting edge density estimation techniques from machine learning, we obtain diluted parameter constraints with respect to a Gaussian likelihood analysis for the same inference problem. And, this is only actually for the same number of simulations that we have available, for example, in the Quixote simulations, a very modest sized data vector, and the number of parameters in our model that's, very much, normal for these kinds of experiments. This was actually all done with a DES year 3 size data vector. But the good news is, based on these results, we can see that SBI is actually doing what it says it does, given enough simulations. So, given what's required for analyses of large-scale structure statistics, this gets a lot worse when you don't know how to summarize your data optimally. That's kind of like the important part of this whole paper, I think, given that you really need to be doing compression for SBI. It's even worse when your covariance has a strong non-diagonal structure here, or you use a neural network for compression. I didn't talk about these results, and I can, later if people are interested. And, this will get a lot worse if there are many nuisance parameters. And obviously, if your model is complex and nonlinear and your likelihood's non-Gaussian. But yeah, that's kind of everything I wanted to show today. Thanks very much for listening. And yeah, this was all done with some software I wrote in JAX. So check it out if you're interested. Thank you very much.
Thank you very much. Thanks for also sharing this repository link at the end. So question, from the audience. You can unmute yourself directly. Jean-Luc, yes?
Yeah, thanks for your talk. But my question would be at the end, would you recommend to use a standard likelihood or SBI for a given large-scale structure survey?
I mean, it depends. If you have, yeah, I mean, it depends. I think I don't necessarily offer a solution here. I think it depends on if you have a theory covariance or not. So in the case you have like a, let's just say you're in this example with a simulated data covariance, like SBI is definitely useful for speeding things up and for example, doing all of this. I think the main point is just that you can't do better than a Gaussian likelihood analysis. So if you can do it without doing it, I don't see why not. And it's mainly a question of speed with some of these machine learning applications, I think.
So I have another question. Why do you say you cannot do better than a Gaussian likelihood analysis, as we know that the likelihood in general is not Gaussian?
So what I mean by this is, so SBI cannot reconstruct a posterior with, so let me go all the way back to here. So this blue contour here is basically the best you can do, right? This is accounting for the noise in your data covariance. And, this is quite an obvious statement, don't get me wrong. But I'm just saying that SBI cannot give you a posterior with, smaller, lower posterior widths than this blue contour here for the marginals. Unless you have access to your data covariance, the true data covariance.
No, but in practice, we never have access to the true.
Yeah, of course. Yeah.
So the question is, for a given survey, we have data, so we can run simulation to get a covariance matrix.
Yes.
Or we can use SBI.
Yeah. I mean, if you know your likelihood, you can just use obviously just do a Gaussian likelihood analysis, right? But I think I'm kind of talking, bridging into the uses of SBI when your data is non-Gaussian as well, right? Like this, you can't expect this to work better than assuming a Gaussian likelihood necessarily. So I would just go with a Gaussian likelihood analysis in these cases for this, for the experiments I've spoken about.
Okay.
Okay, thanks. Somebody else? Anybody else?
Then I will ask another question.
Sure.
Oh, yeah.
Nobody asked question. So when you use a summary statistic and you said you cannot do better, there is a kind of assumption here is that your simulation are perfect, right?
Yes. Yeah.
So you have a dependence on your simulation in your summary statistic.
Yeah. So I'm not, maybe I'm missing something, but yeah, I think like, all of these experiments are certainly idealized in that we, generate our data from the same likelihood as our simulations. In practice, this is obviously not true, and this is what this whole model misspecification stuff is about. But yeah, sorry, what was your question?
Yeah, but then my question would be, do you have an idea how the model misspecification could impact the controls of bias?
Yeah, I mean, I think it's inevitably, I would go with it just simply being a bias. I think it would just simply be biased. Like your machine can't really do anything about that, right? It can only fit the likelihood implicit within the simulations at best.
Okay, thank you.
Okay, then I don't see any other hands up. So thank you very much again then for your time, your talk, and see you everybody next week. Bye, everybody.